Welcome to the start of our study of inferential statistics. Remember, inferential statistics is where you do some computations on a sample, but then you make claims about the larger population from those computations. And of course, anytime you're using a sample to make claims about the population, you're not absolutely certain, so it's always dependent on a probability. So we now start with the concept of confidence intervals. Suppose I gather a random sample of 500 Brookdale students' ages. I compute the sample mean and get 26.1 years. Would you be more confident in me saying the average age of all 11,000 Brookdale students is 26.1 years, or the average age of Brookdale students is between 23.1 and 29.1 years? Think about that for a moment. So if I drew a number line and marked this point as 26.1, or would you be more comfortable with me saying that the average age is exactly 26.1, or if I moved 3 to the left, got to 23.1, and moved 3 to the right and got to 29.1, and said that it's somewhere in here, somewhere between these two, instead of specifically exactly that point? Most people would likely say that they'd feel more confident with saying it's between 23.1 to 29.1 because it gives you some leeway. For example, if the average age is actually 25, then if you said that the average age was 26.1, then if it's 25, that's not correct. Whereas if you said the average age is between 23.1 and 29.1, well, 25 falls in that interval. So this right here, this concept of instead of using a specific point, using an interval instead, is what we call confidence intervals. We first need to start with defining several things. We call the sample mean a point estimate of the population mean mu. Remember, population mean mu is the mean of all of the data, whereas x bar is the mean of a subset of the data. It's also true that x bar is an unbiased estimate of mu. This means that while x bar is an approximation of mu and is likely not exactly mu, it in general does not underestimate or overestimate what mu is. Hence, it's called an unbiased estimate. So in the previous example, x bar equals 26.1 is a point estimate of the population mean age of Brookdale students. Then in the previous example, we said instead of just using 26.1, perhaps we'll give an interval of numbers and say that the mu falls somewhere in that interval. An interval centered at x bar is called an interval estimate of mu. So that example was the average age of Brookdale students is between 23.1 and 29.1 years is an interval estimate of mu. The distance between x bar and the ends of the interval is called the margin of error. Many of you have probably heard, for example, a presidential poll on CNN, 40% approve of the president with a margin of error of 5%. We are going to actually establish what that margin of error of 5% actually means in these coming sections. So again, the average age of Brookdale students is between 23.1 and 29.1 years, has a margin of error of 3 because the distance between 26.1 and the endpoint is a distance of 3 both ways. The reason it's 3 both ways is because the interval is centered at x bar. Do you agree that the larger the interval, the more likely mu falls in that interval? For example, we said that we'd be more comfortable saying the average age of Brookdale students is between 23.1 and 29.1 than just saying the average age is 26.1. But even more extreme, if I used a margin of error of 16, I could say the average age of Brookdale students is between 10.1 years and 52.1 years. That's a very large range, so I'd be even more confident that mu would fall in that extended interval. How confident, though, should we be that mu falls in the interval? The larger the interval, the more confident we would be, but how do we quantify what that means, how confident we are? So that is our next objective, to establish what we mean by we are confident at a certain level that mu falls in the interval that we've created. The level of confidence C is the probability that the interval estimate contains the population mean. So in general, C in all of our problems will reference the likelihood that the actual population mean mu fits within the interval. And you will see as we build these next couple of sections, the central limit theorem plays a major role. Just recall that the central limit theorem says in part that if your samples are of size 30 or greater, then the x bars distribute normally. regardless of how the original data distributes. The level of confidence C is the likelihood that the interval estimate actually contains the population mean mu. We build the interval estimate off of the sample mean x bar. X bar would have a z-score of 0, since it is a distance of 0 from itself. So this means the level of confidence C is the same thing as the middle area underneath the standard normal distribution. So for example, if you're 80% confident that mu actually falls within your interval, that means this area right here underneath the standard normal distribution between these two endpoints of the interval is 80%. So we now need to establish these z-scores that make up the endpoints of our interval on the z-axis. Notice these z-scores are opposites of one another because of the symmetry about the z-score equals 0. These z-scores are so important, they're called the critical values. You can see here by this table that I've already given you some of the information. For example, if this area is 80%, then z sub 0.80, c is 0.80, then z sub 0.80 is 1.28. So in order for this to be 80% of the area under the standard normal curve, this value right here would need to be 1.28, and this one then would of course be its opposite, negative 1.28. If the area you want in here needs to be 90%, then this z-score here is 1.645, and this one is negative 1.645. If you want to be 99% confident, the z-score right here is 2.575. This one is negative 2.575. Notice that I did not give you the critical values for when C is 95%. The reason is because I want to actually do the computation to see where these critical values come from. Once we've done this, you don't need to redo the work that we're about to do to come up with this. This table right here, filled out, including this piece that's missing, is in your test 3 formula sheet at the bottom of the normal distribution table. Let's clean this up here to get started with this. We want this area in here to be 95%, 0.95. In order for that area in here to be 0.95, that means that there's got to be a total of 5% left out in these two tails. But because this 95% is the middle 95%, and because of the symmetry of the standard normal distribution, that means that exactly 2.5% is in each of these individually, because there's 5% in total in these two tails. That means there's 2.5% in each of them individually. So this now amounts to, we need to find the z-score that corresponds with 2.5% of the area being to the left, and that's precisely this z-score right here. If you look in your standard normal distribution in the heart of the table for 0.025, because 2.5% is 0.025, you will see that that corresponding z-score is negative 1.96. Negative 1.96. And because this is the opposite, that means z sub c is positive 1.96. So the positive critical value when c is 0.95 is 1.96. Again, this table does not need to be memorized. It can be found at the bottom of the standard normal distribution table in your formula sheet. Now that we've got the notion of critical values established, we can start to establish the idea of the margin of error E.